This is a video for AQA Mechanics, Center of Mass and Moments, Section 1.2, Introduction to Centers of Mass. Well, firstly, let's consider what we mean by the center of mass of an object. We normally consider that the mass of an object is distributed throughout the object, quite often in a uniform sort of manner. So we define the center of mass as a point at which we can treat the entire mass of the object acting. If you've done any experimental work, then if you had some sort of object, the center of mass would be a balance point. So if you were to balance something at its center of mass, it would stay in there because the moments about the axis here on one side are going to be equal to the moments on the other side. So it's this idea of centers of mass and moments that we use to calculate the position. We refer to the center of mass by the symbol x bar. If we have uniform and distribution of mass and uniform shaped objects, then we can simply use that idea of symmetry to give us the center. So for example, in a straight rod, then we could say that the center of mass is at the center of the rod if the mass is distributed evenly throughout the rod. As I've already said, we can use the idea of moments to find the position of x bar, and we do this by this very simple idea that the moment of the total mass acting at the center of mass is equal to the sum of the moments of the individual masses. So we have this formula that says that the sum of the mass, which is here we have sigma mi, multiplied by x bar, is equal to the sum of each of the individual moments, so that would be mi multiplied by xi. So we get that x bar sigma mi is equal to sigma mi xi. Or quite often we'll rearrange that so that x bar is the sum of the moments, that's the masses multiplied by the distances from the axis, divided by the sum of the masses, in other words, the total mass of the object. Let's consider that idea then for a particular example. Here we've got rods of mass 0.04, 0.03 and 0.02 kilograms respectively, and each of them is 20 centimeters long. So for each of these individual rods, we can say that the center of mass is going to be at these mid positions of the rods. Therefore, the distances involved are going to be 10 centimeters for the first one, 30 for the second one, and 50 for the third one. So now let's put that down into our formula, which says that x bar is sigma mi xi divided by sigma m. So the individual moments then are 0.04, that's the mass, multiplied by its distance 0.1, 0.03 multiplied by its distance 0.3 in total, and 0.02 multiplied by 0.5. We've got to divide that by the sum of the masses, so that's 0.04 plus 0.03 plus 0.02. And if we calculate that, we actually get to a value of x bar being equal to 0.256. That of course is in meters, which is 25.6 centimeters. In this second example, we want to consider a light rod. Now by light we mean it has no mass. So it's not the rod itself which is going to contribute to the center of mass of this system, but it's each of these individual masses which are placed along the rod. So we've got 2 kilograms, 3 kilograms and 5 kilograms placed at 1, 0, 3, 0 and 8, 0. And we want to find the coordinates of the center of mass. Now we can use the idea of symmetry here to realize that the center of mass must be along this line from O. So in other words, the y value is going to be 0. And to calculate the x value, then one way of doing this is to use a table. And here's the table that we can use in this particular instance, where we're going to list the individual masses, their distances xi, and then calculate the individual moments. So the masses are 2, 3 and 5 respectively, so that the total mass there is 10. The distances are 1, 3 and 8. So when we do the multiplication of mi xi, we get 2, 9 and 40, giving a total of 51. And therefore x bar, which is sigma mi xi divided by sigma mi, so that's the sum of the moments, which is 51, divided by the sum of the masses 10, gives us a value of 5.1. And therefore the center of mass is at the position 5.1, and as already discussed, the y value 0. Well, the idea we've just been using can be extended into 2 dimensions, so that we've got now a position of center of mass at x bar, y bar, or indeed we could go into 3 dimensions. You'll see that the formulae are basically the same, that for x bar we've got the sum of the masses in the x direction, the sum of the moments in the x direction divided by the total mass, and for y bar the sum of the moments in the y direction divided by the total mass. So here we have a typical sort of example. This time we've got a light laminar, so by a laminar just mean a plane object. It's light, in other words, it has no mass in this particular case, and the fact it's a laminar means it has no depth into it. So it's a modeling sort of idea that we use. And attached to that are the masses P, Q, R and S, and these are given by the coordinates here, their positions and their masses. So the idea of a table, as we used in the last example, can be used here. This time we'll have x and y directions to think about, and we're going to take our axes as OA, the x-axis, and OC in the y direction. So we want to find the coordinates, in other words, relative to the point 0 here. Well, here's the table that we can use. So you can see we've got the masses P, Q, R and S, which are of size 6, 3, 8 and 5, giving a total mass there of 22. The X values are at 4, 1, 7 and 10, and the Y values at 2, 4, 3 and 1. We first want to calculate the moment in the x direction, so that's the mi multiplied by xi, and gives us 24, 3, 56 and 50, so that we have a total moment there of 133. And then the moment in the y direction, mi multiplied by yi, 12, 12, 24 and 5, giving a total of 53. Therefore x bar which is sigma mixi divided by sigma m, is 133 over 22, which is 6.05 to 2 decimal places, and y bar, sigma mi, so yi this time, the moments in the y direction, divided by the total mass, sigma mi, and that will be equal to 53 divided by 22, so 2.41. So therefore we have a centre of mass at the point 6.05 and 2.41. So there you can see nicely, neatly written out on a table, and you see how using the table helps to organize the working, so that really at the end of the day you just have quite a straightforward calculation to do here. So in summary then, we've got the idea that x bar is sigma mixi over sigma m, the sum of the moments divided by the total mass. We're often going to be using a light laminar. Light simply means it has no mass, or a light rod to hold things in place. And then in 2 dimensions we can extend the idea to give us a coordinates of the centre of mass x bar and y bar. And finally, although it's not strictly necessary, it is a useful way of organizing your work to do it in a table. That completes this video on centres of mass, and in the next one we'll be looking at the idea of the centre of mass of a laminar.